Okay, so in this lesson, we will represent exponential functions. And use them to calculate unknown values. I don't know why all of a sudden my voice is starting to go away, so just be patient, please, or I request your patience. So let's talk about linear functions. Linear functions and exponential functions. All right, so linear functions, they come in, you can write it in slope-intercept form, you can write it in standard form. The way that you're most familiar with is y equals mx plus b, y equals mx plus b, where this is your slope, and this b is your y-intercept. So, and let's review that for a second. So parent linear. So this is like the OG, the original parent function. This is the basic one. And that's f of x equals x. That's just y equals x. So if you look at this, I can get that. Okay. If you look at this, then our parent function, the parent of all this, has a y-intercept of 0. And it goes up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Or that helps us find more points, right? And if you look at the table, we start at 0, 0. I guess I can do that. Okay, so we start at 0, 0. And then this is our change in y, and we'll put our change in x over here. And we add 1, up 1, right 1, up 1, right 1. Oh, we can even go backwards. We would go down 1 when we go left 1, or Now, exponential are going to be different. If you notice here, we're just adding, right? That's why it's going to be different. We'll see. So exponential functions. So the general form is y equals a times b to the power of x. There's different ways you can write this. You can put more, you can make it more complicated. This is all you need to know right now. So let's write that. Let's make blue. So y equals a times b to the power of x. Now there is no parent to this thing. There's no original one, so to speak. I'll give you an example though. So we'll do 1 times 2 to the power of x. So if you notice, we start at 1. This is where we start. And we don't see this nice, even constant rate of change, constant rate of change, constantly changing by the same thing. That doesn't happen here, really fast, like a hockey stick or something. This is, let's do, that 2 is our multiplier. So in our table, we start at 1. You see how we start at 1. But this is let me do this. Actually, I'm going to do that's fine. So in this right here, if I try to add, it's plus 1, plus 2, plus 4, plus 6, plus 8. And then I get plus 16. There's definitely a pattern here. I can see it, right? And this one is plus 1, plus 1, plus 1. But that would be, there's a simpler way of showing this. Because you can see a pattern 1, and then so on and so forth. But there's a much easier way of showing this. Exponential Oh, let me get rid of that. There we go. Exponential in and of itself means we multiply. That's where we multiply right there. We have a, like multiplier. So this is actually times 2. And then we take that times 2. And that times 2. And that times 2. You see? This one is plus 1. So every time we move by 1, we multiply by this 2. So, and so on and so forth. And like backwards, instead of multiplying by 2, we would divide by 2, because that's like the opposite. Like here, instead of adding, we subtracted. So divide by, oh wait, we just minus 1, because this is plus 1, so the opposite is minus 1. Minus 1, this will be divided by 2. Okay, this is going to help us. Actually, before we get to that, that's why, like, see how we're multiplying by 2? So, like, bam. Like, 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. You can see that, oh, I guess I can show it like this. It starts to increase quickly. That's because we're multiplying. So if anyone ever says you're getting exponentially like more, it means it's going up very quickly. You're multiplying. If you're losing exponentially, you're losing very quickly, So compared to constant rate of change, at least. All right, so next page. So in this first example, Jami decides to become a microbiologist. She notices that there are 400 germ cells in a petri dish. The number of germs increases by 25% each month. How much or how many germs would there be after 6 months? So let's figure this out. So there are 400 germs to begin with. And the number of germs, the germs increases by 25% each month. I can maybe do a little better. I hope I can do better. One more. Man, I came so close. Every month, and I'll stop there, and then I'll continue. There we go. Okay, so how much will there be after 6 months? I should use a different color for that one. Let's use blue. So, first thing I want you to do is let's create a table, right? So germs. So we're talking about germs and months. Germs and months. We have germs is what we care about after months. So germs, months, germs, months. So I'll put 0 months, 1 month. It wants to know 6 months, 2, 3. I should leave some space. I'm pretty sure I'm gonna need it. Okay. Now we start off with 400 germs. That's good. And it increases 25% each month. Now that's the part we got to think about. Like we can't just do like plus 25%, nothing like that. So if we add 25%, I want you to think about it. This is all of that we have. This is already 100%. And then we're going to add 25%. Okay? So in reality, we're trying to calculate 125%. So if you move that and convert it, you get 1.25. So we're actually multiplying by 1.25. And then multiply by 1.25. That's all we're doing. So I'm going to do that. So 400 times 1.25. let's see. So 400 times 1.25 is 500. So I get 500. And then I multiply by 1.25 again. 500 times 1.25. And I get 625. And I just keep doing that. Times 1.25. $781.25. Make sure you show this at least twice so I know that you're doing it over and over again. So 781.25 times 1.25 is 976.5625. $965, is that it? No, 565. 565. Okay, times 1.25. Oops, I need to type that whole thing in. Maybe if I copy it. Times 1.25 equals 1220.703125. You won't do this many on your work. I just wanted to show you something, an example that gets ridiculous. And then we'll take that times 1.25. And I'm just going to estimate 1525.88. Just make sure that when you do this, only estimate on the last one, because if you estimate here, you'll get the wrong answer here. Like, if you estimate here, like put 781, then this will be more off, then this will be more off, then this will be more off. So if you're going to round on the last one. All right, so let's write some equations. So we care about the germs. So I'm going to say the germs start off at 400. And we kept multiplying by 1.25. And we did that. I'm going to do that all in red. We multiplied by 1.25. Like one time, then two times, three times, and four times. So it changes, right? So we'll just put based off the number of months. Like if you want 2 months, you'll multiply it by it twice. Like if you want 4 months, we start with 400, we multiply it by 4 times. So we'll put times the number of months. Now, another way that you could write it, I usually make them write like 4 times, but don't worry about writing it 4 times. I'm just going to have you write it twice. So you could also say that the germs are a function of the number of months. You start off with 400. And then I want you to write it like in this weird way that we added it. So you start off with 100%, which is 1. Ooh, I should do this in a different color again. You start off with 100%, which is 1. And then you added 0.25 or 25%. And you did that times the number of months.